So one of the foundational pieces of software that we have in the networking project of OCP is Open Network Linux. And Jeffrey leads the Open Network Linux subproject. And he's going to talk to us today about what it is, why you should use it, and what they're going to be doing in the future. So take it away, Jeff.
All right. Can everybody hear me? Take that as a yes. Let's see if this works. All right. So this talk is about Open Network Linux. My name is Jeff Townsend. I'm VP Engineering at Big Switch Networks, and I am the original inventor and current benevolent dictator for this project. So if you have any questions about it, I designed most of it, and so I could probably answer anything that you'd like to know. First of all, what is it? Open Network Linux is a Linux operating system and distribution for bare metal switches for open networking hardware. You got to do a lot in order to actually just get something running on anything, and Open Network Linux provides the foundation for that. You can read the marketing blurb here about all this stuff, but the real question is, what is it? What's its purpose? And if you think about starting from a piece of hardware, and then you want to actually run something, you want to get some switch software, you want to get some data plane, you want to do anything at all, well, you got to put some software together. You got to put a whole lot of software together before you can even write your first part of your data plane, right? And the purpose of ONL is to provide that environment to get you started on any piece of open networking hardware. Open Network Linux is a subproject of Open Compute. It's available on GitHub in the Open Compute community, and it is the reference operating system for all OCP hardware. If you want to submit your design and have it accepted as OCP hardware, it must also support Open Network Linux. Right now, there are about 120 platforms that are supported. You can go right to the GitHub, and you can see all of them, from Acton, DNI, Delta, Quanta. I put them in alphabetical order here, but I'm just reading them from my brain. Lenovo, Facebook. The full HCL, you can go there. I can't do it right now, but you can see whether they're accepted to OCP, what their form factors are. We've got switches that are, Tomahawk, Broadcom, Mellanox, Barefoot, pretty much all the guys. Pretty early on, when you decide that you need to support a lot of different switches, if any of you are old school, you remember that most of the switches that we all started out with were like PowerPC. If they weren't PowerPC, they were even worse. They were like ARM, like an integrated ARM processor from somebody like Broadcom or something like that. So it's nice for everybody now to just think all of the OCP hardware and all of the switches being made now are all just easy x86. Don't have to worry about all that stuff. But that's not the way it is that's not the way it is outside the data center. You still have this low-cost hardware. PowerPC is dying for a lot, but you still have ARM coming up, x86 predominantly everywhere, and low-cost ARM for 1 gig switches. Even for production, new designs today are still low-cost ARM integrated switches. So ONL is designed to work on all of these platforms, and so it provides an infrastructure that allows for multiple architecture support. We support x86, PowerPC, ARM, both variants. Every once in a while, someone wants to support PowerPC 64, and if you have some kind of interest in that, you can talk to me. So multiple architecture support. The deployment model, we wanted to make sure that you could do a stateless deployment model for giant fabrics, and a regular deployment model where each individual system has a stateful installation with local configuration and stuff like that. So there's two different models. One which allows you to build a system that is completely stateless on the switch each time it boots, and one that allows you to install your software and make it persistent along with this configuration on the switch. Both of them have their advantages. The other options we wanted to, in order to make it easy, because we have 120 platforms across 4 architectures, is you can't have one image for every single box. You can't have an installer for every single box. You can't have, right? So we have one image that for each architecture, and you have to be able to support every platform that's in that architecture. So one of the design goals is polymorphic platform support from the beginning. The ONL project started out as part of something that Big Switch just did to build our own operating system, just like Cumulus was building their own, like we were the only guys doing it, right? And at some point, we decided we should share this part. And so when we broke away our internal version of ONL and made it public, it was important that it become brandable and customizable. So there are hooks inside of it for you to brand it as your own OS, you know, your own customization strings, your own names for your stuff. I don't know, brandable and customizable. And then finally designed as a base layer for your OS. So if you go to ONL now, there's a script in there that just says, make me a new OS. And it gives you everything with all of your abilities to put all of your own names and all of your own parts together and give you the entire infrastructure for you to build your operating system based on ONL without it saying ONL. So these are some of the design goals to make it usable by everybody else, not just some fork-off copy of the way that I do things. So if you kind of look at an OS, right, any of them, you need a kernel. Well, this doesn't apply to all of them. Everybody needs a kernel. In ONL, we need a kernel. We have a kernel. We have what we call a loader, which is the first initRD that is the first thing that is booted up after the kernel. We create a root file system that's based on Debian, and we selected Debian because of all the distributions, they support the most architectures. And it's just only recently that they've dropped some important architectures like PowerPC and stuff like that. But at the time, you know, if you wanted to support PowerPC and x86 and MIPS, I mean, like there's nothing MIPS now, but like at the time, you could still have some MIPS processors inside some old switches from Broadcom. So widest architecture support. So we use Debian, and on top of that, because the switches are not servers and they don't have standard hardware, and the hardware that is inside them is all very, very specific. We have our own APIs on top that we call the ONL platform APIs that give you access to everything that is inside the switch in a consumable way by software. The kernels that we use are LTS kernels. So even though we use a Debian distribution, we use LTS kernels so that we can more easily incorporate CVE updates, and so that platform vendors don't have to be tied to the current kernel used by the Debian distribution that they're currently on. Whenever there's a CVE, you know, we try to update. Whenever there's a new release of an LTS kernel, we update the kernel in ONL. We incorporate all of the CVEs that are fixed in there, and we move forward from there. We don't have a lot of time, so I'm going to skip through some of this. One of the important things for ONL is that the platform implementations, because there are 120 of them, for example, the platform implementations can't conflict with each other. So while we try to share the same kernel on each architecture, and in the previous slide you've seen that you know, we scrutinize the changes to the kernel very carefully, and we don't allow them unless absolutely necessary, and unless they guaranteed not to mess with other platforms. The kernel is shared, but everything else is separate. So if you have a special driver for your CPLD, for your fans, for whatever it is, you have to provide it as a kernel module that would then compile against whatever kernels that you are selecting for your platform. And those modules are never loaded on any platform other than yours. So there's an infrastructure in place to segregate your code from every other platform's code, even though the root file system supports all of the platforms of the architecture. So we have strict boundaries on where code can execute and where code gets stored, so that we can reliably take patches for one platform without having to worry about it conflicting with some other platform. OK, so we have a kernel. We have some kernel modules if your drivers need it. The first thing that happens when we boot ONL is the initrd is loaded, and we call it the loader because the loader, it's an initrd, but its purpose is to decide what kind of root file system to boot. Now, in a normal case, you'd have an initrd, and it would just find the root partition on your disk, and it would do some stuff, and then it would just switch root to that, and then you would see that your system 5 init or your system D or whatever it is would start running. And most people don't even see it. There's an initrd, but there is. It's usually the first thing. Sometimes it's built right in. It's in a different partition. Ours has additional functionality in that you can use it to select whether or not you can use it to select a different switch image, a different root file system on the fly. So there's some functionality for getting switch images over the network, some functionality for getting them from local storage. You can interact with the loader and load different images, play with the box. It's basically the first thing that decides where is the root file system that we're going to execute. After that, we have to build a root file system. So it's great that we can go load one, but how do we do it? Like I said, they're based on Debian, and the ONL tools have basically ability to create a prepackaged base of standard Debian utilities, all the stuff that you need to actually, bash and ls and all the bin utils and everything you need to actually make a Linux system. And then it has the ability for you to add your own packages to it based on your operating system. So this is the exact same technology that we use to build our commercial product. So we use all of this infrastructure all the time. So the ability for ONL to build and then have packages added on from outside that are not public, that are not open source, that are private from our repos and stuff like that. So you basically use the tools to cater the contents of your root file system, and then the ONL tools will just build it for you. Like I said before, the root file system building is one thing, and then the root file system using is another, right? And so in one case, you have the root file system, and you want the switch to use that, but you don't want any changes that are made to be persistent. So for that, we have a model. It's called the switch image model, where the whole root file system is delivered as a squashfs, and using some trickery with memory, it's loaded, but any changes to it are not persistent through a reboot. You can also take that file system and just spew it out onto a disk like normal distributions do, and it becomes like a normal Linux box. All right, I think we said that already. Switch images. So I'm going to move forward a little bit because we have a little bit less time, and I want to leave some time for questions. The important part about everybody can understand like spitting it out onto the disk, but the important part about the switch images is it's delivered as a squashfs, which is read-only, and then we do some trickery where we mount that and we put a memory file system on top of it using the overlayfs in Linux, and that makes it look like it's a read-write file system, but all of the changes are discarded because every time you write to a file, it's only into memory. And every time you read a file, as long as it's not to a portion that's been written, it comes from the compressed squashfs. So once all of that's done, it just looks like a normal Linux box, and you don't have to worry about it. Some of the reasons why we do this, and this is how we deploy in our commercial product, for example. If you mess up something on the box, you can just restart it, and you get back to the way you started, right? If you want to upgrade all of the boxes at the same time, they can all just download a new image. You don't have to reformat them. You don't have to worry if somebody has messed up something on one of the boxes. So it's a clean slate every time the switch boots. And for cases of upgrade, it can be a clean slate. It can be a different image every time the switch boots. So it's good for things like fleet management, and it's good for rollback. So the other thing I want to talk about are the ONL platform APIs, and these are a set of APIs that create a standard API across all of the different FRUs and SFPs and fan controllers and all these things that are different on all these boxes. If you've ever worked on one of these boxes or written any software for one of these boxes, you already know what a hassle this is. So, but you have to have it, right? The data plane's sexy. That's what everybody wants to work on. But If you can't get your fan speed up, then your box might die. So super important, not interesting, nobody wants to do it, and it's different on every box. So one of the things we've standardized in ONL are a set of platform APIs that allow all of that stuff to be accessed. For example, your data plane needs to know, has an SFP been plugged in? Well, SFP being plugged in is different on every one of those 120 boxes. Different, not the same, different. Different I2C trees, different number of muxes, different ways that the connectivity of the signals come in, different CPLDs, different on every box. Right? And somebody has to know how to do that. And so if you're the guy doing the platform for a box, you're just going through a doc, you're just doing it again, doing it again, doing it again. But there's no room for innovation here, right? Everybody wants to know how to read the EEPROM of the SFP. Nobody cares how you do it, right? We're not going to like invent a new way where it's like better, right? So what we did was create an API where all of this is standardized, and the vendor, who is the one who knows how to do this, provides the implementation, right? Anybody can provide the implementation, but the goal is that we provide a standard interface, and the vendor, who's the guy who knows what his CPLD looks like, Acton knows what their I2C tree looks like. They're the ones that provide all the guts, and then you as an application developer just use one API on every one of these boxes. And the API says, is there an SFP? I would like to read the SFP, right? Tell me the fan speed of this fan, right? Not what fan speed controller is there and what is its I2C address, and can I talk to it, and is somebody else talking to it at the same time, and should I not do that, and that sort of thing. So it's tremendously valuable. It allows all of these boxes to work. It makes it getting your software up and running on these boxes like super fast, and then only one person has to do it, and God bless it. So the other thing that we have is, like I said, polymorphic platform support. So due to this segregation between all the platforms, we also have a system in place that allows you to select all of the platform collateral at boot based on what platform it is. So every image has, a directory of collateral for each platform. These are the modules that should load. These are the libraries that implement all of those APIs I talked about. These are the special settings these are the other things that need to be set up. These are the SysFS files, whatever it is that you need. We have that all segregated for each platform, and it gets selected at early boot time. And then after that, when your application runs, if you use the ONLP APIs, you don't even have to know anything. You can just ask it. You can ask it to enumerate all of the objects that are in the system. So you can build your software independent of which platform it's on, because you can query the platform at runtime. Did I mention that it works on all the platforms? Because it works on all the platforms. Just no small feat. The other part is orchestrating all of this takes a lot. If you want to support ARM and you want to support x86, you want to support PowerPC, and if you've ever tried to do it, anybody here ever try to build a tool chain? Anybody here ever try to do it twice? Right? Sucks, right? Sucks, right? So the ONL build environment needs tool chains for all the applications, for all the architectures. It needs libcs for all the architectures. It needs all of the packages that are going to be in the final system. It needs all of those for linking and library building and all that stuff. So what ONL provides in terms of the build environment is all of that stuff in one Docker container. So you can build for Jesse or for Stretch based on which Debian distribution you do. And there's a corresponding Docker container that has all of the tool chains and all of the libraries and all of the dev packages in order for you to build code, cross-compile, so that you can target that platform. So you want to cross-compile PowerPC SNMP agent, you do it on an x86 in this Docker build environment, and then magically it works on the PowerPC runtime that is on your switch image. And so this takes all the hassle of you're not going to go download something and install it or whatever. You just pull down the Docker. There's one tool, it's called ONL Builder. You run that, it puts you in the Docker, it's interactive, gets you all the stuff you need, and gives you every tool chain that is needed to build every single thing in ONL. So here's a page of resources. There's the GitHub project. So all of this code is open source. It's some of the Open Compute under Open Network Linux. There's a documentation page. It's not super great right now, but it documents mostly those ONLP APIs, so you can start looking at that. Homepage, the HCL, which I had before, shows all the platforms currently supported, and some other stuff. That's all I got. I think that's on time, so if there are any questions.
Yeah, so we can take questions, and if you do have a question, please use one of these two mics that are standing here in the middle of the floor so that your comments or questions can be recorded.
I see I've converted you all.
Thank you. Hey, how about the extension for the platforms? If they have a specific attributes in some platforms, right? Is the APIs have an extensions?
So the current API, and do you mean like for platform objects? Like, are we talking about the ONLP stuff? What's the domain of your question?
The ONLP APIs are there, right? If I have a special, let's say I have a special coprocessor in my, or something like that, right? Is there an extension API to the platform APIs? If I want to support my box, right, it has a special thing which is not there in many of the boxes. There is no current API in ONLP for that. So is there a way for extensions?
There is. So the current API was designed originally for pizza boxes that we're familiar with. So there's one system EEPROM. There's just one set of SFPs. You probably don't have a lot of pluggable modules and stuff like that. So there's a new version of the API that we are publishing now. It was actually published last year. But it hasn't been completely ported yet to all the platforms. But we call it the V2 API, and that's designed for all of the extensibility that you'd like to have. So it has an interface that allows you to have arbitrary, get sets on objects that you can define yourself. And so you can expose, if you're familiar with the API, you can expose your custom object as a generic OID, and then you can retrieve and assign attributes to it. And so it provides a channel for anywhere in the OID hierarchy for you to insert your custom hardware.
And for some of the cases, you need to access the NPU as well, right? That's it for some of the capabilities of the platforms.
So you have to access the what?
For the switch ASIC. So how does it happen in ONL if you want to support that?
So the operation of the data plane, or the ASIC SDK, or whatever it is for the most part outside the scope of the platform APIs, because it requires access to usually the vendor SDK, which is not something that's public. You could do something with SCI, right? Like if there was some data that you wanted to manipulate through SCI, which was public. So it's a case-by-case basis for whether the public code can access it.
Thank you.
Was there a question over on this side?
No, I was asking, can you repeat the question?
Oh.
But I guess I understand the question.
Okay. So along that line, a lot of platforms now have BMCs on them. And they're running some sort of code, maybe OpenBMC or some other code. Does ONL have the ability to communicate with the BMC to report what fans are present or what speeds they're running or things like that?
Yeah, so the part of the functionality is limited by what the IPMI definition for the BMC allows or exports, right? And so on some platforms, you can also read the devices at the same time that the BMC, but you don't want to do that. It's a big hassle, and it doesn't work out right. So for the platforms with BMCs, the model that we've had thus far is the ONLP layer will provide all of the same objects, but it will query the BMC over IPMI. And there's an IPMI cache. And so a lot of the original implementations would just go get the fan speed. And so it would actually be a lot of overhead to talk to the BMC just to get one fan speed, right? So there's a lot of batch operations that you can do and say, just go give me all the sensor data. And so to keep the semantics of the API, where you can query any piece of data at any time, but still make it responsive. And if you're familiar with talking to BMCs, it artificially increases your CPU rate while you are communicating with it. because of the way the drivers work. Underneath the hood for platforms that implement it properly, we create a cache of all of the IPMI data, either the sensor data or the FRU data, that's updated asynchronous to the application's request. And so if you go ask for a fan speed, it reads it out of the cache, and you don't have to wait for the IPMI refresh. And you don't have to wait to go talk to it, and however long that, like, in terms of software, it's an enormous amount of time to go just read the fan speed. And so IPMI cache is kept secretly, and then the results are updated at some rate that you care about, and then the API functions the same.
Any other questions?
Yep. Telemetry analytics. What is the roadmap for that?
Pardon, what is it?
Telemetry and analytics APIs.
For the platform? Like, so the ONL itself supports SNMP. So all of the platform APIs for all of the FRU status and all the FRU values, presence, failed. So that kind of telemetry is available out of the box using SNMP. There's no data plane integration here, so I can't give you any data plane telemetry.
Okay.
The whole goal of this is to give you the base of all of this stuff that needs to work that you don't want to use, right? That you don't want to do because you're worried about how do I implement the best data plane telemetry, or what is the data plane model that I want? Is it a BGP fabric? Is it some special FBOSS thing from Facebook? Is it what Big Switch does? Is it the data plane is what's important to you, but you can't get there until you have all this other stuff.
Okay, thank you, Jeffrey.